Okay, class chapter 7. So in chapter 5, we did the simplex. And remember that was an edge traversing or exterior point algorithm. We moved from one basic feasible solution to another, always in a direction of improvement until we could no longer improve and could prove that we were at the optimal solution, or we could prove that lambda was equal to infinity, was unbounded. Okay, so now what we're going to do in chapter 7 though is whole new paradigm. We're going to now move through the interior. So if you had X-ray vision, we're going to start at some point on the interior, just like the simplex. That's not always easy to get, but some problems it is, and we have a whole nother way of getting it. So X-ray vision, we're somewhere through the inside, and we're going to move through the inside step by step, always improving, always maintaining feasibility, always maintaining that we're in the interior. So that's an additional condition this time. Before, for the simplex, our additional condition was that we were an extreme point, one extreme point to the next. Now in the interior point method, we have to add the condition that we are actually in the interior. And we don't want to get to the exterior outside until the very last step. So we always want to sort of be repelled by the boundaries of this until we're at the last step, and then boom, we're right at the extreme point if that's the optimal solution. Okay, so whole new paradigm, just a few things to review. An interior point, if your problem is in standard form, always your equalities are active, and you're an interior point if none of your inequalities are active, right? So there's nothing you can do about the equalities, but if your inequalities, the x greater than or equal to 0 part of the standard form, if none of those are satisfied, so they'd all be x greater than 0, right? There's not a single point x equals 0. Then you're in the interior. Easy thing to check then. And then we also have this bit of review. We know for an LP that the direction of maximal increase, the optimal direction to move in, is the gradient, which is just the C vector, or vector of coefficients. And if it's a minimization, then we do the negative gradient. Okay, so let's take a look at these ideas on a couple figures. I want to look at figure 7.1 on page 386 and 7.2. Okay, here's 7.1. There's a small, this is an example in R2. So we have a x1, x2 variable, and we can plot it there. This is before standard form where we have to add any variables. Here's the contours, right? And they say, let's focus on this first part, x0. An initial interior feasible solution is 1/1/2. And again, it's clearly in the interior of the picture, but we could also look at it just algebraically by saying none of those components are equal to 0. So therefore it has to be an interior solution, interior feasible solution. Okay, and then this is the direction C of maximal increase in this problem. It's a maximization problem. This is the C vector then. And notice from our Calc 3, we know that this is always, these directions are always perpendicular to the level curves. So we see that visually as well. And you could always do a dot product in higher dimensional space with your C dotted with the level curve vectors. And you'll see that that has to be the case, that they're 0. Okay. Oh yes, so the next statement, that at an interior point, so x0 is an interior point here, any delta feasible so long as lambda is small enough, right? Remember, our iterate rule is x1 equals x0 plus lambda times the delta x. And so here's our delta x, we're going to go in this direction. How far do we go? That's the lambda. So as long as lambda is small enough, anything, and that makes sense. At any interior point you have, in this case, 360 degrees, you can move all the way around. In higher dimensional space, anywhere that you can move is feasible. So the delta x, anything's feasible, but we'd really like to move in the direction of C. Now, what happens if we do that? And typically, like with the simplex, we said, okay, well, how do we get our lambda? You take the biggest lambda that maintains feasibility. Well, that would send us all the way up here to x1. What's the problem? For an interior point method, we don't want to be at x1. I'm sorry, we don't want to be at an edge. X1 is on an edge or a boundary. We don't want to be at those boundaries. We want to stay interior. until we get to X star, which is over here. So that would actually violate one of our ideas for the interior point method. And so let's look at the next figure. Figure 7.2, same problem. Here's our X0, here's our X star. And what actually happens when you run an interior point method is this might be the optimal direction, but we're really going to stay towards that, but we're also going to sort of project or perturb the problem a bit so that we can stay repelled by the boundaries each time. And so like it's getting closer and closer to that boundary, but then it never touches it. And we'll talk about how we do that repelling with the projection step. Okay, and here's the principal interior point algorithms begin and move through a sequence of interior feasible solutions, converging to the boundary only at the optimal solution. So only at the last step. Okay, so standard form LP, when we are doing an interior point method, again, this is the one we want to worry about. We want to actually make sure every iterate is X strictly greater than 0. Okay, so here's something we've learned. We know from chapter 3 that delta X is feasible if and only if A delta X equals 0. You solved that a whole lot when you did the simplex. That was the key step. We know it's interior if and only if this holds. Again, your next iterate, and the previous example we just did X0 plus lambda times that delta X has to be strictly greater than 0. But we also want improving. So we have to talk about how we're going to do improving with this additional condition that we are repelled by boundaries. So that's next. So erase the board and get there. Okay, we're going to do this with something called a projection step. It's a topic in linear algebra. Many of you may not have gotten to it unless you're in a graduate linear algebra class towards the end. So the idea of projecting, you may have done it in a calculus class, a very basic type of projection. If you're in three-dimensional space and we have a vector, you wanted to project it onto a plane or say the XY plane, you're really just pushing that thing down into the XY plane. And that's the same idea that we're doing here. We're trying to find a vector, delta X in n-dimensional space, that satisfies these conditions, A delta X equals 0. That's similar to the condition that you wanted to push this vector into the plane, right? And closest to C, right? Remember that's the best direction to go in. The problem was if we go in that direction too far, we're going to get to a boundary. And therefore, once you're at that boundary point, you now have to consider feasibility. You can't just think about improvement. You have to think about feasibility as well. We like to simplify it and say, if I could just stay interior, I don't even have to think about feasibility. I know I'm in the interior. And so we want to satisfy two things, that your A delta X equals 0 and you're closest to C in the least squares sense, which really just means you're minimizing the difference between the optimal C vector, the delta X vector you're choosing, in a least squares sense, which just means the two numbers. So the difference, the sum of the squares, difference of those makes a vector, and the sum of the squared components. Square root of the sum of the square. Okay, so here's the key thing. This is the main thing we're going to do over and over. This is a box on page 392, box 7.6. The projection in the direction D. So we want to go towards, ours is going to be, we're going to replace C and D with C. Onto the conditions A delta X equals 0. That preserves, we're doing this because we want to preserve AX equal B. It's given by this statement here. Delta X is P times D. Okay, but P is the projection matrix, and that takes quite a bit of work. This is a formula to memorize. It's the identity matrix minus A transpose, AA transpose, inverse A. So that right there is a lot of work, right? There's a matrix multiplication is O n cubed, an inversion of that is O n cubed, two more matrix multiplications. So several O n cubed pieces of work. But let's break it down. I mean, that seems pretty messy, but we'll see that that is the main expense of an interior point method. It really boils down to this. Just like in the simplex, the main expense boiled down to solving this homogeneous linear system. We had to do that over and over. Well, in the interior point method, the thing you're going to be doing over and over is computing this projection matrix. That's your big expense. Oh, the other thing I should say about interior point methods. So simplex versus interior point. They're both going to solve the problem. For some applications, a simplex is probably still the favored tool that's used over and over, especially for small to mid-sized problems. The interior point method, though, has gained some favor for very, very large problems. It takes many fewer iterations, although the work per iteration is much, much more than one simplex iteration. One interior point method is much more work. One interior iteration has much more work than simplex iteration. Require much fewer interior points, but it's heavy work per iteration. Also, there's other applications in which, simplex versus interior point. Well, for my research, there's some applications where I love using the interior point method. And we'll get to that actually. We'll learn a little more and I'll come back to that. Remind you. Okay, I want to work this example though. I think this will help put in context what we're doing with this P, this projection matrix. Okay, we have a small example of 3 variables. It's already in standard form, right? Equalities and non-negativity and simple constraints. And they ask us to do several things. There's several parts to this. In the first part, they say, find the direction of most rapid improvement. So we already know that's just your C. Part A, the most rapid improvement will come with the C vector 4 minus 1. So in part B, they say find the projection matrix associated with this. And maybe even give us okay, so they say in part B, find the projection matrix for this. However, I want to point out, I think I have this example from the old edition, so it's really not 7.7. This is just an unnamed example for us. But we can still answer all the parts of the question. Part B, find the projection matrix. So P is going to be, I'll write it in MATLAB code so you can put it in and check. So we need an identity matrix. We need A. So over here on the side, what is the A matrix associated with this? There's 3 variables, Z1, Z2, Z3. A is 1, 0, 1, 0, 2, 0. So a 2 by 3 A matrix. And then we're going to do 2 by 3 by 3 by 2, the transpose 2 by 3, and then 3 by 2. So it all results in a 3 by 3. So we need a 3 by 3 identity. All right, so if I've stored this in MATLAB, the A matrix, I can just say P is then I for identity. We want a 3 by 3, so you just say I3 minus A primed as the transpose times, and then I would need to put in parentheses the inverse of A times A prime times A. And that'll spit out this matrix, 0.5, 0, minus 0.5, 0, 0, 0, minus 0.5, 0. So you can do these. This one's not too bad to do by hand, but some of them just get slightly bigger, and it does help to use your, if you like to use a TI calculator to do these matrix multiplications or MATLAB, very easy. Okay, then question C. Apply the projection to the direction in A. So they actually say get the direction vector. Delta Z for us would be P times C. So you just go ahead and do that multiplication. In MATLAB, you'd say P times C, right? And you get this vector. Minus 1/2, 0, 1/2. I'm sorry, 1.5, 0, 1.5. Okay, and then in part D, they say verify that this actually is improving and feasible. All right, so how do you check if it's feasible? How do you do that? You take, show that A delta Z equals 0, right? That's our box 3.25 that we use several times. If this is true, direction's feasible. If the direction is feasible, this is true. It went in both directions. So just go ahead and do that multiplication and you'll see it's not bad. Yes, you do get this matrix times this vector. First row, yes, that's going to go to 0. second row times this column, yes, that's 0, so check. And then how do you show it's improving? If C times delta Z is greater than 0, because we have a max, right? And here's our C, here's our delta Z. So we'll have C times delta Z is negative 4 times negative 1.5 plus 0 plus 7 times 1.5, which is clearly bigger than 0. I don't know the decimal. So it's improving. Okay, and then they say, describe the sense in which the direction vector we got, delta Z, is good for an improving search at any interior point solution. And we know it maintains feasibility, we know it's improving, and it is as close as we can get to the most rapid improvement, C, while still doing those things. So it maintains feasibility, stays in the interior, is improving, and is the closest thing we can get to C. Okay. All right, so there's a few problems at the end. I want you to look at numbers 1, 3, 4A, B, C, and D. Okay,